In this lecture videos, I will be talking about the competencies and objectives of investigating alternative energy options. And for this next 2 or 3 lecture videos, I will be talking about, in this case, wind and solar power. Okay, so this is actually the main focus. So if you remembered, and you probably do not, one of the problems that we're currently encountering is the amount of carbon dioxide emissions that we have in the current atmosphere, and which is in this case is affecting global temperatures and global climate as we know it. Okay, so if you look at this like at this graph here, this is actually in the left axis. Okay, in the left y-axis, this is actually telling you how much, in this case, megaton of energy we're actually currently making, and in this case this is actually how much gigatons of carbon dioxide we're actually emitting. Okay, so under current policies, okay, what happens is, as you can see, the amount, this is the blue, is actually the amount of carbon dioxide emissions. The amount of gigatons of carbon dioxide that we're going to be emitting is still going to be increasing. Okay, under current policies, primarily due to the decrease in coal and oil-based power supplies, we actually have been, it is forecasted that we're actually slightly declining. The amount of carbon dioxide is going to be declining. Okay. However, as we know, this is not enough. Again, the key number that we have to think about is the 2 degrees Celsius increase. Okay. Post-industrial levels. And so in sustainable development, we actually need to decrease. We actually do not want this slight increase. We want the actual amount of carbon dioxide emissions to actually decrease. And obviously that can only be accomplished by, in this case, decreasing or eliminating, okay, the power generation capacities for our fossil fuel based, okay, power supplies. So in this case, decreasing the amount of coal that we're burning, the amount of oil, and the amount of, in this case, natural gas that we're actually using. Okay, an interesting thing in all of these videos, in this graph, if you can see it, is actually the amount of nuclear power is actually predicted that if you want a sustainable development, we actually need to increase it a little bit. Obviously, the problem with that is there's been a great fear about the dangers inherent in the generation of, in this case, energy via nuclear power. But obviously a big component of the future energy mix in sustainable development is an increasing amount of energy created through renewable, in this case, sources of energy. So we're talking about, in this case, solar power, wind power, geothermal, so on and so forth. Okay, so this is the reason why we need to start thinking about renewable energy sources. Okay, so just to show you, and this is a very outdated model or graph in this case, in the year 2007, right, a small proportion, 7% of our total energy, in this case energy capacity, is actually created through renewable sources. Okay, and this is British thermal units. You probably know that that's actually how much it is to actually, in this case, combust a ton of something. Okay, and if you look at the proportion of renewable energy sources in this case, the big component of our what we term as renewable energy is actually through biomass. Okay, a small proportion is wind, a big proportion is obviously solar. Hydroelectric is a big component of it, and geothermal is also like a very big component of it. The problems with hydroelectric power is hydroelectric power requires damming of waterways in this case, which obviously in this case affects the way that rivers and water flow. So obviously you're going to have, in this case, some inundation or some flooding of areas that are usable. This is actually already happening in China. So that is a big problem there. Obviously, livestock like fish is affected, so on and so forth. The other thing is biomass, which is a big component, 53%, dwarfs almost everything in here. The problem with biomass is biomass comes from plants, okay? And plants or other, in this case, living things. And so the problem with biomass is still carbon-based. So anytime we burn biomass, we're still, in this case, emitting carbon dioxide. The only reason why we call biomass renewable, okay, even though it still emits carbon dioxide, is biomass has a very short, in this case, generation time, right? So if we're gonna burn some, in this case, wood, right, from a wood pile, it takes like a few years for us to, in this case, grow a tree, cut down the tree and use it, and that is the reason why it's actually termed renewable. This is obviously different than when we use coal and other fossil fuels, which takes hundreds of millions of years to actually be generated, right? So again, the problem with this is we still have carbon dioxide emissions, right? So we're going to start first with wind power. So wind power, FYI, is actually generated. So wind is actually generated, interestingly, via the sun. Okay, so the sun creates areas of the earth that actually, in this case, areas of the planet that are warmer or colder, are warmer than other areas which are colder. And what happens is, because of this differences in temperature, you actually have wind movement, right? So tsunamis, okay, tornadoes, all of those, in this case, great manifestations of wind power are actually the reason why that we actually have those great manifestations of wind power, is because there's differences in temperature. So what happens is wind, okay, normally will actually blow faster, right, from like in this case, going from warm to cold direction. Okay, so that's what we call the cold front or the warm front or whatever you call it. All right, so that's how that is. So so there are two types of wind turbines. We have, in this case, we have vertical wind turbines or horizontal wind turbines, and obviously horizontal wind turbines are actually the most prevalent, or the most, in this case, I guess, in fashion trend for harvesting wind power. Right, vertical wind turbines are actually not very much used. It's actually only used in experimental, in this case, experimental fashions. Okay, there is actually another type of wind turbines which is currently on the horizon, and those are called bladeless wind turbines. Okay, so that is something that's just an FYI. Okay, you don't need to know those. Okay, but so again, we have horizontal and vertical wind turbines again. So horizontal is the prevalent one. So this is a generic, okay, schematic of how in this case, how a horizontal wind turbine actually works. So you obviously have normally 3 blades, and 3 blades is actually the most famous design, and the reason why that is because you actually have a higher efficiency when you have 3. We have 3 blades. Hypothetically speaking, however, the most efficient type of wind turbine would be a single blade. But obviously there's going to be problems with the way that single blades are distributed in terms of weight. So you're going to have problems if you're going to install that in a very raised area, right? 3 is actually it's actually an engineering, in this case, scenario in which it's actually like the best scenario in which we can actually both get enough energy from wind and at the same time not affect aerodynamic functioning of the wind turbine. Okay, so 3 is the most famous. 3 blades is the most famous. So what happens is wind normally hits the blades, and the pitch is basically just the angle of the actual blade to the wind. The slower the wind, the flatter the pitch, or the flatter the blade is relative to the wind. Okay, the faster the wind, the more, in this case, basically the less flat the actual surface of the actual blade is towards the wind. Okay, and obviously the reason why that is because you don't want high winds to actually make this blades turn too fast, and obviously creating a engineering catastrophe in this case, right? So that's actually what that is. So the problem, however, most of the time, okay, so I already talked about speeds, right? So any speed above 50 miles per hour, the actual pitch of this actual blade will be feathered, or it's going to be straight on. So the sharp edge is going to be towards the wind, and what happens is that creates, in this case, a slow turning, okay, instead of in this case, high speed. And obviously if you have a high speed again, you're going to create an engineering catastrophe. Okay, slower the wind, the flatter the angle of the blade, right? And again, the faster the wind, the more sharper it is, right? So that's that. However, in most instances, we know for a fact that wind speeds are actually low. So what we need to do is we need to convert that low blade speed into fast mechanical energy, and the way that we actually make the slow turning of the blade into a faster turning to actually create, in this case, mechanical energy is through this gearbox. And so what happens is normally the proportion is 1 turn equals 90 turns at the back end of this gearbox. Okay, and so because now you have a higher mechanical turning at the end, now you actually now convert that mechanical energy into electrical energy, and obviously that electrical energy is in this case actually stored in batteries. Okay, so that's actually what the main thing. The yaw drive and the yaw motor, okay, is actually connected to the wind vane, and what happens is obviously you need to aim the blades towards wind direction, and so the wind vane detects the changes of direction of the wind, and when the wind vane turns, it makes the yaw motor turn towards, and the yaw motor then in this case turns the blade towards the direction of wind travel. Okay, so that's the only thing. All right, there are always emergency brakes, again, because you don't want in this case a runaway blade. Okay, that's going to be a problem if that's the case. All right, so that's one of the schematic diagram of in this case of a wind turbine. Now the wind speed is variable. Okay, so depending, the lower you are to the ground, the slower the wind speed, generally speaking. The higher you are, obviously the faster the wind speed. And it also there are also many other components, topographical, or in this case geographical concerns. So obviously if you're actually in a valley, okay, and wind is generally coming through the mountains, you're going to have less wind. But if the wind is actually traveling through the valley, you actually have a better instance in this case of getting actually wind energy. So there's a lot of topographical things that you have to understand in this case, right? So you actually don't want to build a wind turbine very, very close to the ground, because and then if you have trees around the area, obviously the trees is in this case going to dissipate the wind speed. So in that case, you need to like have your wind turbine way up high. All right, so that's the main thing. So energy effectiveness. So energy effectiveness is basically all we're talking about in this case is kilowatt hours of electricity or kilowatt hours of therms. Okay, this is actually just energy measurements, and grams of carbon dioxide per kilowatt hours for electricity. So therms is not considered in this case. So as we can see, if we use coal, we make a very, very small amount, and blue, by the way, is the electricity, and the red is actually how much carbon dioxide. When we use coal, we actually emit a lot of carbon dioxide per kilowatt hours of electricity. Okay, hydropower, again, is very efficient. You have a very, very small amount of grams of carbon dioxide, and you actually have a high amount of electricity. And for photovoltaic or solar energy, in this case, you actually have, in this case, you can see there's almost equal, right? The amount of carbon dioxide that you emit is almost the same amount of kilowatt hours of electricity that you actually emit. So, and obviously this is relatively speaking to each other. Okay, so that's actually a ratio in this case. So in this case, you actually also have wind, and wind actually has a very small amount of carbon dioxide relative to, in this case, how much electricity you actually create. Now the ratios here, just to let you know, is obviously if you're at 1, that means to say that the amount of kilowatt hours is equivalent to the grams of carbon dioxide that you emit. The higher you are in this ratio, okay, depending on this, that means to say that either the higher the amount of carbon dioxide that you actually create, or the higher the amount of electricity that you create. So that's actually the take home of this diagram here. So there's obviously a lot of challenges for wind technology. One of the main challenges of wind technology is this thing called the Betz number. And that means to say that a wind turbine can only convert 59.3% of wind speed into mechanical and electrical energy. Okay, that is the max. And I'm not going to talk about engineering here, but just know that you can never convert 100% of the wind speed into energy. And obviously this is, in this case, quite true for all energy transformations. Okay, there are a lot of new things that's going on right now. There are new sensors. Okay, what happens is you can actually, instead of like controlling just one wind turbine, what you can actually do is you can actually control multiple wind turbines at one time using in this case, a area control system. Okay, I am going to be stopping this this video soon, and what we're going to be doing is I'm going to be continuing with wind energy in the next lecture video.